So now the next thing to do is to think about two objects coming to thermal equilibrium. And what we're going to do is what we've been doing, try to predict the most likely partitioning of energy between these two objects at equilibrium by calculating the number of possible microstates, and the arrangement of energy that corresponds to the most microstates is the thing we're just going to see the most often. There are just more ways to do it. So I remind you that last time we did a calculation for what was it? Two atoms, and well, we got a histogram that looks something like this. We had this axis was Q1, the number of quanta in object 1, and this axis was the total number of ways of arranging energy between these two objects, and we found that one was more probable. There were just more ways to partition the energy equally. Well, we want to do this with bigger objects, okay? So we're going to use the same approach to calculating things, but we want to do it with particles that are sort of semi-realistic sizes. And so we're going to start out with, we're just going to let a computer do the calculations for us. We're going to talk about a total two objects that have a total number of oscillators that are 500, and I know that's not evenly divisible by 3, but we're in the noise here. And one object, what do we got it set for now? Okay, so one object has 400 oscillators, and the other one only has 100. Okay, so this is object 1, that's object 2. And we're going to put the total amount of energy is 100 quanta. So if these are aluminum particles, this is 100 times 3.96 times 10 to the minus 21 joules. And we're just going to see, we're going to calculate the number of microstates if there's 0 quanta in this one, the number of microstates if there's 1, 2, 3, and we're going to go all the way up to 100, and then we're going to plot it. And what we get is a histogram. It looks like this. So let's figure out what this histogram means. Turn the lights down a little bit so it's easier to see. So the x-axis is what? Number of quanta, the amount of energy in block 1 measured in quanta. Okay, so it's basically energy, but it's just measured in number of quanta. And the y-axis is actually this product, omega total, the total number of microstates that there were corresponding to that. So you calculate the number of ways of arranging 0 quanta in block 1 and 100 quanta in block 2, and you plot it here. And we go on up, and we see that there certainly is a most probable that at least down here we can't see any probability. Now that number might not be 0 because this number is 7.5 times 10 to the 114th. So there are really a lot of ways of arranging energy. The calculator, I think, can't quite do this one, although we're close. But what we see is that in this case, the most probable situation seems to be that There's what, 50, 60, 70 something here. 80%. So it looks like 80% of the energy is in this block and 20% of the energy in this block. Is this surprising? Not really, is it? Yeah, there's just a lot more places to put the energy. Yes. Not necessarily, because no, it doesn't actually work that way. And if they're not, because it's not actually, well, it's going to work out this way for a while, but what if they're, but you're going to run into a lot of complications. So what if this block is made of aluminum and the other is made of iron? Oops. Yeah, it's going to work out the way you think it ought to, probably. So let's try a different partition. Let's say we have block 1 has 300 oscillators and block 2 has 200. So what do you think? What do you expect? Yeah. Okay, so this is 3 and that's 2, and in fact you're seeing what you expect. So yeah. So I mean, no big surprises, right? Here, but there is an issue that these numbers aren't zero. They're small, but they're not zero. And in order to see what it really looks like, one of the things, these are big numbers, one of the things we could do is just plot the logarithm. Instead of plotting the number of microstates, we could just plot the logarithm. And what that'll do is just expose the smaller numbers, and we can see where things are zero or not. So this is the same plot, except plotted with logs. And now there are two different things on this plot, so we need to explain. So this axis is indeed still Q. This is the log of the number of ways, but we've actually plotted two things. So the plot that corresponds to this histogram, where we're just taking logs, is actually this magenta one. This is the log of the total number of ways of arranging the energy. And we can see that it actually does have a maximum at exactly the same location. So in this case, it's 60%, right? So this is the same thing we're seeing here. What are these other two things? Well, they're going to be interesting. This red one is just the log of the ways of omega 1, the ways of arranging however many quanta it is in block 1. And the blue line is the number of ways of arranging however many quanta are left in block 2. And the way logs work, omega total was the product of omega 1 times omega 2. So the log of omega total is the sum of the log of omega 1 plus the log of omega 2, right? Okay. So we have omega total was the number of ways of arranging Q1 quanta in block 1 times Q2 quanta in block 2. So the log of the total number of ways is the sum of the logs. So it's okay. And if we try a different partition, so let's go back to or let's make it go the other way. We'll make it 100 and 400. So we'll change that to 100 in block 1, oscillators in block 1. That leaves 400 in block 2. And we get these two plots, and not surprisingly now, the bigger block gets most of the energy, yada yada. And now the maximum of this quantity here is at the same location. Now the interesting thing about that is that it turns out that what we're really plotting here is nearly the entropy of this system. Entropy is a concept that people doing classical thermodynamics on macroscopic systems had come up with a long time before people knew there were atoms and started thinking about ways of arranging energy in microscopic oscillators. But what it turns out is that the entropy of a system, the way the classical thermodynamicists had defined it, turns out to be exactly the same number as this. So S is the symbol for entropy. And on a microscopic level, you can calculate entropy by this equation. We have the log of the number of ways of arranging the energy, the number of microstates, okay, so and there's just a constant here. It's called the Boltzmann constant. It's named for Ludwig Boltzmann, who figured this out. And the value of the Boltzmann constant is 1.38 times 10 to the negative 23rd joules per Kelvin. And there's so many K's floating around here with interatomic spring stiffnesses and whatnot that the convention is usually these days to call it K sub B for the Boltzmann constant. And so we can actually now say something a little more formal about what we expect for equilibrium here. So we expected that at thermal equilibrium for this situation where we had 100 oscillators in object 1 and 400 oscillators in object 2, we expected that we'd get 20% of the energy in object 1 and the rest in object 2. We can say that a different way, though. We can say that at thermal equilibrium, the entropy of the system is a maximum. So this leads to a number of different ways of thinking about equilibrium and the approach to equilibrium. So you've heard of the laws of thermodynamics. You may even know what they are. The first law of thermodynamics really is just the energy principle. Change of energy of a system is W plus Q. The second law of thermodynamics talks about equilibrium, basically, and it says if you take a system, whatever objects you're going to put into it, and you isolate it from the rest of the world, and you wait long enough, the most probable thing that will happen is that it will end up in a state where the entropy of the system is a maximum. So, and that just corresponds to more different ways of arranging energy, more different possible ways to put all the energy. So systems, an isolated system, if it's not in equilibrium to start with, it's going to eventually equilibrate to a situation where the entropy is a maximum, and that means that the entropy of the system increased. So people sometimes say the entropy of the universe can't decrease. And the most probable thing is that it'll increase because energy, once it gets, and this has to do with irreversibility. So we've talked about the fact that it's really not very probable that the moving atoms in this table will all move up in such a way that they make this pin jump up into the air. once the energy's gotten distributed among all the oscillators and all the atoms in the table, its entropy is at a maximum. It's very unlikely that it's going to revert to some distribution where most of the thermal energy in the table is in the atoms right under the pin. So, yes, it could happen. It's not impossible. It's just so improbable that we would have to wait for longer than the age of the universe before we were really likely to see it. Because the probabilities of having, it's the same as having the probability of all of the energy that we put into it be in the block with 100 oscillators. It's not impossible. It's just so improbable that we don't really ever expect to observe it. Yeah. I don't think it has anything to do with spontaneous combustion, actually. That has to do with drummers. But okay. So the most probable thing is that the entropy of the universe, or the entropy of a system, will actually increase.